Today we will be covering sinusoidal functions. 1 radian is when the distance traveled around the circle is equal to the radius. So as you can see in the diagrams, it's when you take the length of the radius and wrap it around the edge of the circle, and that length is your radian. So essentially all 3 segments seen here are the same length. A radian is equivalent to 100 degrees over pi radians, or about 57.3 degrees. We're going to begin by graphing a cosine function. So as you can see here, I am just determining the a, b, h, and k value from the function after I factored out the b value. Factoring out the b value makes it easier to see what the b and h value actually are, and in this case the h value is a positive 2. The amplitude is just the absolute value of a, which is 3, and the period is 2 pi over the absolute value of b, so that will equal a 2 in this case. Now to determine the tick marks, you're going to take your period and divide that by 4, which will give you a 1/2. So now we are going to start at our h value, which is a positive 2. So we're going to start at 2 and just add 1/2 to that to get each tick mark. So we're going to start off at 2 and then add 1/2 to get 2.5. And we're going to repeat that process by adding the width, which is 1/2 again and again, which could be 3, 3.5, 4, 4.5, and so on. So now we're going to label the axes. And since our k value is a positive 5, we're going to go up 5 units and mark that to determine our new x-axis. And we are also going to keep in mind the amplitude, which is 3. So we're going to go 3 units above and below our new x-axis, which is 5, to determine the minimum and maximum of our cosine function. So now we are just going to label the x-axis with our tick marks that we found. And what you can also do, since 2 is far away from the origin, you can subtract your tick mark width, which is 1/2, to get as close as you want, as close as you can to the origin in this case. So subtracting 1/2 will give us 1.5, 1, and 0.5. And then we're going to go ahead and label from there, starting with our lowest tick mark value. So now to graph, we're going to start at our h value, which is a positive 2. And since cosine does not go through the origin and the parent function, we are going to be starting at our maximum value, which is 8. So we're going to put a dot there to indicate that, and then we are going to follow the cosine wave from there. So then we'll hit through the x-axis and then hit our minimum value and continue that wave pattern. Once you mark all your dots, you can go ahead and connect them to create the finishing cosine wave. And you can draw arrows on the end to indicate that it is a continuous function. So that is how you graph a cosine equation. So now we are going to be graphing a cotangent equation. As you can see here, I yet again factored out the b value to make it easier to determine the b and h value. And in this case, the h value is negative, so it's translated to the left pi over 6 units. So from there, we can determine the period, which is 2 pi over 3, which will give us the tick mark width if we divide that by 4, or multiply by 1/4, and that will give us a pi over 6. So now to get the tick marks, we're going to start at our h value and just add pi over 6. So that will give us a 0, then pi over 6, and it's pretty easy to determine that from here. So now we're going to go ahead and mark our new x-axis. So we want to look at the k value, which is positive 2, and to go up 2 units to make our new x-axis. And since our amplitude is 2 as well, we're going to mark 2 units up and 2 units down. Now we're going to label our tick marks, starting at our h value, which is negative pi over 6, and then just use all the tick marks that we found. So now, since this is a cotangent graph, we need to graph the sine function first to get our asymptotes. So since sine starts at the origin, it's going to cross the x-axis the first starting place, so that's negative pi over 6 in this case, and then just graph the sine, and every time it crosses your new x-axis, you want to draw a line to indicate an asymptote. So now you can actually graph your cotangent equation. So you're just going to put a dot at between the two asymptotes. And then as you can see, you're going to do a decreasing pattern shown here, which will determine that it is a cotangent. And this is how cotangent graphs look. This is why it was very important to mark the quote-unquote minimum and maximum so you know where to draw all your dots when graphing cotangent equations. So that is how you graph this equation. The last graph we're going to be graphing is a secant. And as you can see in this equation, we also factored out the b value to make it easier to see what the b value and h value is. So the h value here is 2 pi, and the k value is a positive 1. So our amplitude is the absolute value of a, which is 2. Our period is 2 pi over 3, so that would make our tick mark with pi over 6. So now we're going to start at our h, and as you can see, our h is very far away from the origin, so I am going to put that as our first tick mark. But if you count backwards from 2 pi by pi over 6, which is the tick mark width, it will eventually get you to the origin. So I'm actually going to start at the origin and add pi over 6 to that. So as you can see, I'm marking new tick marks. This will just make it a lot easier to graph, and it will look better once you do graph it. So I'm just adding pi over 6 to all the values, which if you keep going, you will eventually reach 2 pi. So you have to make sure to double check yourself if you are doing it this way. So now we're going to label our graph and mark our new x-axis, which in this case, since our k value is positive 1, it's 1 unit from the actual x-axis. And then we are going to go ahead and also mark our amplitude, since it's 2 units above our new x-axis and 2 units below. This will give us our maximum and minimum for the cosine or sine function we'll be graphing, which is a cosine in this case. So now we're going to go ahead and label the x-axis with the tick marks we found. So I'm just starting at my pi over 6 and going from there. And as you can see, I think we're going to be ending at 8 pi. So if you just were to continue this, it will reach a 2 pi very evenly. Each tick mark is just pi over 6 units apart, and you will reach the 2 pi. So now to graph it, as you know, cosine does not start at the origin. Cosine starts up. So you want to start at your starting point, which will be the origin in this case, but typically it would be 2 pi. They act as the same. And then you're just going to graph the cosine to get all your asymptotes. And now secant graphs look like quadratics in the case that they are parabolas facing up or down. So at the minimum and maximum of your cosine graph, you are going to be drawing parabolas, and I'm going to show you what I'm saying here. So that's the top of your cosine graph, and then you go through the x-axis, and then you hit the bottom. You're going to draw another dot, and as you can see, you're just following the cosine wave. So now from there, you can draw your parabolas, and the parabolas always face away from the x-axis. So that is how you graph a secant equation. So now we're going to be solving a angular velocity and linear speed word problem. So a windmill with a 90-meter diameter makes 15 revolutions per minute. What is the speed of the windmill? So we are going to find the angular velocity in radians per minute at the tip of the blades, and then find the linear speed in meters per minute at the tip of the blades as well. So first off, from seeing that there's a 90-meter diameter, that means the radius is 45 meters. So we are going to begin with finding the angular velocity in radians per minute. So we know that it makes 15 revolutions per minute, so we are going to put 15 revolutions over 1 minute, and then we need to put the bottom of the other side 2 revolutions to make it equal. And as we know, 1 revolution equals 2 pi radians. So we are going to go ahead and put 2 pi radians over top of 1 revolution. And as you can see, revolutions cancels out here and it leaves you with radians per minute, which is the units we want. So 15 times 2 pi is just 30 pi radians per minute. So now to find the linear speed, we can see that it is actually asking for a measurement, which is meters. So we are going to take the 45-meter radius, and as we know, to find linear speed, you can use angular velocity. So we are going to take the angular velocity, which is 30 pi, and multiply that by our radius to find the linear speed. So 45 meters times 30 pi will go ahead and give you 1,330 pi meters per minute. And that is how you find the angular velocity and linear speed in a simple word problem.